And let me just find the place where we took off from. If you may recall, in the very first class, by the way, YouTube video is already uploaded to the YouTube channel, and you can find it by the link in the WhatsApp group. We are almost there. Here it is. Characteristics of polynomial function in factored form. This is where we finished. Remember, we discovered there is a family of polynomial functions that are going to have same x-intercept points. And what defines those families is the coefficient in the brackets in a factored form. And this family can be different according to this coefficient, leading coefficient. Whether this leading coefficient negative or positive will give us corresponding properties for the given polynomial function. And factored form, indeed, one of the most important forms of polynomial functions, because, as we discovered in the previous class, we didn't finish this unit, right, in the previous class. We just started it. So, knowing that we have a factored form of a polynomial function, let's move ahead to the problem that's going to show us how can we use this factored form of a polynomial function. For an instance, we can calculate the y-intercept easily using it. How to calculate the y-intercept? So if you remember, the y-intercept is such point that crosses the y-axis, right? Here or here or here. Basically not crossing, but lays on the y-axis. So in order to calculate y-intercept, we should take x equals to 0, right? So basically it's going to be at the beginning of the coordinate axis. So we substitute x equals 0, which in factored form makes it super easy to calculate the result. You see, 0, we just simply ignore it and we look at the remaining terms in the equation. And we can see that 2 times minus 1 times minus 3 squared, pretty simple to calculate. And as a result, you're getting 18, which means the y-intercept is going to be at y equals 18. So this is point 18. And for example, this function, which is a fourth degree polynomial functions, and you can see that by the number of terms and the exponent. So this is the first degree, second degree, third degree, and square here tells us that this is basically fourth degree altogether. You also can see this on this drawing down below. Remember that the fourth degree polynomial is going to have 3 turning points. Remember, number of turning points is 1 less than the degree of a polynomial function, and number of x-intercept can be as much as degree of a polynomial function. In this particular case, we have only 3 x-intercept, and let's go ahead and look into that, how to find this x-intercept, because we already found the y-intercept 18, and how do we find the x-intercept? Basically the same approach, but now instead of substituting x equals 0, we're going to substitute that y equals 0. And you can see that our function becomes just a standard equation with one unknown variable, right? You can see here 0 equals negative x plus 2 times x minus 1 times x minus 3 squared. And basically, how can this equation be equal to 0? It can be equal to 0 when at least one of these brackets that we have here equals to 0. This should be pretty logical to you, because if we are multiplying terms by one another, you see, all of the terms are multiplied. There is no addition or subtraction between the terms in factored form. So when one of the brackets equals 0, so for example, first bracket equals 0, second bracket equals 2 or 3, wherever, but 0 times 2 is 0, and now 0 times 3 is 0 again, right? Makes sense? So now we can come up to conclusion when at least one of the brackets equals 0, then the y would be equal to 0 too. And what solutions, what possible solutions may we have here? Looking into the first bracket, what value of x should we take in order for this bracket to be equal to 0? Any ideas? Okay, guys, of course, I believe you can see that x should be equal to -2 in order for this bracket to be 0. Second bracket, x minus 1. What value of x should we use here in order to get 0? 1. 1 minus 1 equals 0. And as well as final bracket, x minus 3 squared. So what value of x should we take? We should take x equals 3 in order for this bracket to be equal to 0. Is there any questions about that, how to use factored form in order to find x and y intercepts of the function? Okay, I believe it means no questions. So why are we doing this? First of all, we're doing this in order to sketch this function without using graphical calculator, right? So now we already know all the intersection, y-intercept, x-intercept, all three of them. But what are we supposed to do next? So we don't know the shape of the graph just yet. We just know this y-intercepts and x-intercepts. So now we have to use the value of x that fall between the x-intercepts as test values to determine the location of the function above or below the x-axis. Since the function lies below the x-axis on both sides of x equals 3, the graph must just touch the x-axis and not cross over at this point. The order of 2 on the factor x minus 3 squared confirms the parabolic shape near x equals 3. So, right, basically what we see here, x minus 3 bracket, is a parabola itself. So it confirms that parabolic shape near x3 should be present. That's why we have only one. That's why we have 3 x-intercepts instead of possible 4 x-intercepts. For an instance, if we would have another bracket here instead of x minus 3 squared, we would have x minus 3. There would be no square here. And we would have one more bracket, x plus 5, for example. This would give us another x-intercept. But as soon as it's quadratic, we should be seeing parabolic shape near x equals 3. Also, so what we're doing in this step, we're using the values of x that fall between the x-intercept and test values to determine the location of the function above or below the x-axis. For example, here we take a point to the left-hand side from -2, right? This is one of the x-intercept that we found. We take one value of x to the left from this point, and we can see that we're getting some kind of negative number. So it means that for these values of x, function would be in a third quadrant. Third quadrant, right? And then we take one value to the right-hand side from -2, but before 1. So basically, what we're doing with using the x-intercept, we're splitting our domain of a function into several intervals. These intervals are splitted by the x-intercept. You see? So first x-intercept -2, second x-intercept 1, and second x-intercept is 3, according to what we discovered in the previous step. And now, last thing we have to do is to take at least one x value in each of these intervals. For example, For values less than -2, it would be -3. For values between -2 and 1, it would be -1. For values between 1 and 3, it could be 2. For values greater than 3, it could be 4. You see? And by using those numbers, we can identify in which quadrant is the function located for specific values. Here you can see that from -2 to 1, function allegedly positive, right? 32 value. So our function, this interval corresponds to positive values of this function. Then we can see that before -2, function is fairly negative. So we can see this interval going down. And also it gives us an end behavior of the function, right? It's going to negative infinity. Then interval from 1 to 3 gives us negative number again. So we know that from 1 to 3, function is going to be negative. And you can see it on the graph as well. Then from interval 3 and greater, we can see that the function is still negative, which implies to what we can see on the graph that function travels to the negative infinity. You can also come to this conclusion knowing that this is an even degree polynomial function, which means it is going to have similar end behavior on both ends. Okay? So determine the end behavior of the function. How we do it? Because the degree is even and the leading coefficient is negative, you can see it here, minus in front of the brackets. The graph extends from third quadrant to the fourth quadrant. That is, as x plus minus infinity, y would always be negative infinity. This is a possible graph of f of x estimating the location of the turning points, right? Because we're not quite sure where these turning points are going to occur because we didn't study them. We just know that the function is going to cross the x-axis in this point, it's going to cross the y-axis in this point, x-axis here again, and here. We also know that it's going to be traveling to negative infinity on both ends, right? So this is one of the possible graphs that we can sketch through these points. But remember that this graph could have a different shape, for example, like this, going up, then going down here, then going lower here, going up, and going down. This is also a possible shape of this curve, but with a different turning points because we didn't identify them for this scenario. These are suggested turning points. Using reasoning to determine the equation of a function from given information. Before we move on, do you have any questions on that, how to sketch a polynomial function using everything we learned up till now? Okay, I assume you don't have any questions. Moving on to example number 2, we know that we have to write an equation of a cubic function that has zeros at -2, 3, 2 over 5, and the function also has a y-intercept of 6. So cubic function, right? Cubic function implies degree 3, third degree for polynomial function, right? So we already know that our polynomial function is supposed to have the following form. F of x equals k times x minus a times x minus b times x minus c. This is the general form that we're supposed to have in this example. We also know that the function has zeros at x -2, x3, and x2 over 5, and y-intercept of 6. Okay? So what it implies, let's start with the zeros of the function. Remember that these values in the function a, b, c, they are actually responsible for what zeros we're going to have. So if our zero is x equals -2, it means a in this bracket should be -2, right? Because if a is -2, then in the bracket we're going to have x plus 2 and x equals -2 would give us one of the zeros, right? As well as for the second bracket, if x equals 3 and we have a 0, it means that b should be equal to b should be equal to 3. Because we have minus here, we're going to get x minus 3, and 3 is another intercept in 0 that we have here. Is it clear? How do we find terms in these brackets? And finally, if we have a factor form like this, 2/5, basically, what do we have to do? We can do it in the following way. We can say that x times 5 minus 2 would be our bracket, or we could even say x minus 2/5. This would be our bracket. Now, knowing that, we're getting our 3 brackets, but we still don't know the leading coefficient, right? There is no information about that. So let's talk it through. Use the zero of the function to create factors for the correct family of polynomials. Since this function has 3 zeros and it is cubic, the order of each factor must be 1, right? Makes sense. And now, how do we find this a coefficient? Because we know the function has y-intercept of 6. We can use this formula and simply say that if x equals 0, because that's how we get our y-intercept, this function f of x equals 6, right? And that's what we're writing here. 6 equals a times the bracket, but we already substitute x for 0, or 0 for x. And you can see that it's pretty easily to calculate this leading coefficient when you know the y-intercept and you know that x equals 0. You substitute x equals 0, you get 2 times -3 times -2. You open the brackets, you get 12a. 6 equals 12a. Moving 12 to the left-hand side will give us a equals 1/2, right? After simplification. And as a result, we have the complete function for the given polynomial function based off its zeros and y-intercept. Isn't it fascinating? So now you can create a factored form of any polynomial function using only its zeros and y-intercept. Any questions about that? Because this is really important part. If you don't understand this, later on, you're going to struggle with your assignments. Guys, please give me your feedback so I know what we're doing here. All clear. Thank you, Safa, for your feedback. Anybody else? Do you have any questions? May I move on? All good. So all that we are doing is solving for A, correct? No, that's not correct. Solving for A is only one of the steps. First step was to create these brackets of a factored form using the zeros of a polynomial function. Then, in order to complete the complete form of this polynomial function, we have to solve it for A using that y-intercept equals 6. Using this approach, you can calculate the leading coefficient of a polynomial function based on its zeros and y-intercept, if you know them. So in first scenario, we were looking for x-intercept and y-intercept based on the formula of a polynomial function. And in this scenario, we do inverse operation, basically. We're creating a function based on the zeros and x-intercept. Okay. Example number 3 is even easier than the previous one because it's basically based on graphical representation of a polynomial function. Basically, you're already given with the proper polynomial function. What are we asked to do is to write the equation of the function shown below and state the domain and range of the function. Okay? Write the equation, as we did in the previous step, and state the domain and range. And let's begin with simple analysis. What we can see on this graph, we can see that it has 3 turning points, which implies it should be a polynomial function of degree 4 or greater than 4, right? if we have 3 turning points. Also, we can see that the end behavior of this function is same on the both ends of this polynomial function. And it's positive, which implies that this is an even degree polynomial function. So it should be 4, 6, 8, etc. And also the leading coefficient supposed to be positive. That's when it's open upside down, open up upwards. We're also given with one of the points that belongs to this graph is 2, 4. X equals 2, y equals 4. And let's see how can we use this information. So now we have to write the equation. And the reasoning, as I just said, because the function must have positive values on both sides of the x-intercepts, the factors are squared, right? You can see that this function is always positive. Do you agree with me? It never crosses the x-axis and goes down. It's always positive. And how can we get a function that is always positive? By taking square. So both of the brackets supposed to be squared. Also, we can see that we have only 2 x-intercepts, which gives us an idea that we're going to have only 2 brackets. And we know that we have only 2 brackets, and this function should be at least 4th degree. So we raise each of these brackets to the 2nd degree. The factors are squared. The parabolic shape of the graph near the zeros, x equals -2 and x equals 3, confirms the order of 2 on the factor x plus 2 and x minus 3. Okay? Again, we're looking into parabolic shape around the x-intercept. This curve that you can see here, basically a parabola, right? And this is a parabola. Meanwhile, for example, in this case, not always we had a paraboloid shape. We had a paraboloid shape around x equals 3. So, now knowing that we have this point 2 and 4 that belongs to this function, now we can calculate the leading coefficient because we know what to substitute in our function. We already know the terms in the brackets. We don't know the leading coefficient. So if we don't know the leading coefficient, we should know x and y value. That's why they gave us this one point. Because if we don't know x and y value, at least for one of the points, it means that we have too many unknown variables to calculate the leading coefficient. So we substitute x equals 2 and y equals 4 into the function, which are coordinates of the point marked on the graph into the equation. After doing that, we're simply solving it for a now, as we did in the previous example. Again, opening all the brackets, simplifying, and finding out that a leading coefficient is positive, and it's 1/4. Now we can use it to finish notation of our polynomial function in factored form. So we have 1/4 x plus 2 squared, x minus 3 squared. Is that correct? Do you agree with me, or do you understand how I did this? Any question? Okay, guys, I believe you have no questions about that. And we're gonna move on to the second part of this assignment, which is B. We have to determine the domain and range of the given function. Even based on the graph, it's fairly simple to do. All polynomial functions have their domain over the entire set of real numbers. So x value could be any value. Take a notice that this is only related to the polynomial functions. Later on, we're going to look into uh, uh, rational functions, which are basically two polynomial functions combined. And those functions are going to have breaks and discontinuities in their domain. So we won't have all the real numbers. But for standard polynomial function, we have all the time all the real numbers. So x is enclosed in the interval from positive infinity to negative infinity. Meanwhile, we can see that our function is clearly has an absolute minimum in 2 points. So values when y equals 0 based on the graph, right? Y equals 0 is an absolute minimum for this function, the lowest point that it could get. Using those 2 points, we can conclude that y value should be equal or greater than 0 in a set of real numbers. Is this clear? Because this is basic understanding of graphs. And finally, representing the equation of a polynomial function with its graph. Please take a moment, because here we are going to use all the techniques that we used up till now, right? Finding the x and y intercepts, making the factored form of a polynomial function. And I want you guys to sketch a polynomial function for me. Each one of you guys gonna have its own quadrant. So for example, Hala, this is your quadrant. Mohammed, this is your quadrant. And Safa, this is your quadrant. In this quadrant, each one of you should sketch the given function with coordinate axis. Like I can still help you sketching the coordinate axis if you prefer. Safa. So this is for Safa. This is for Hala. This is for Muhammad. Please take a look at this. And each one of you guys, please sketch the polynomial function according to this solution. This is super simple, guys. Super simple. But this is going to be proof of your activity in the class. Okay? Please text okay in the chat if you understand the task. Good job, Safa. Okay, Mohammed. Hala, are you with us? Yes. So go ahead, sketch the graph, and we're gonna get back to the next part of the class in about 15 minutes. So you can do this in a few minutes. I'm telling you, this is not a complicated stuff. And the rest of the time until, let's say, 11:05, you have a break, okay? So you have time to process material that we just did, okay? Okay, guys, I'm back. Okay, I can see Hala, Muhammad did their part, but what about Safa? What's your problem? Okay, so I can see that you got the part how to get the zeros of this function. So you can see that you have 1 0 in x negative 2 and x 0, right? Yeah, so exactly right. You're gonna have one side behavior as a basically a linear dependence, a linear shape near x equals negative 2, since the factor x plus 2 has an order of 1. And basically, knowing that you have two x-interceptions, you're going to cross the x-axis at least twice. So if to the left-hand side, here you can observe the cubic shape, right? We remember that the cubic function has following form. Let me use another color, for example, blue. Cubic function would have the following form around x0, and around x negative 2 we have a linear dependence, right? We also can see that the leading coefficient is positive for this function, so the end behavior is supposed to be positive infinity, as all of you did correct. So for Mohammed, question how to sketch the bottom part of this function. Basically, you know that your function is supposed to be in the third quadrant in this interval, but only thing that you don't know, where does the turning point occurs in this quadrant. But right now we don't really care about where exactly does the turning point located. We're going to learn it later on. So for now, you can sketch an approximate shape of this graph based on knowledge that around x equals 0, around this point, we're supposed to have a cubic shape at x equals 0, since the factor x to the third power has an order of 3, right? So basically, we're combining linear and cubic function together while sketching. So you're gonna have turning point somewhere here, and then your graph should act like a cubic function, like a standard cubic function we covered in the previous classes. And behavior, as we said, positive on both ends. So yeah, guys, you did a great job, and I can see that you can understand how to plot the polynomial function. Mohammed, do you have any questions? Do you have, did I answer your question? Okay, great. And finally, final example. Yeah. In this final example, we're going to look into like kinda real life scenario with a dolphin. While playing in the surf, a dolphin jumped twice into the air before diving deep below the surface of the water. The path of the dolphin is shown on the following graph. So we can see that we can imagine that dolphin was rocking up from underneath the water. He jumped out, he dived in, and he dived out again, and then went deep into the water. We have to write the equation of the polynomial function that represents the height of the dolphin relative to the surface of the water. So we have a graph of the height with respect to time, right? Y-axis is the height in meters, while the x-axis is the time in seconds, okay? So how can we write a equation of this polynomial function? First of all, we are looking at the graph and analyzing it. We can see that it has a similar end behavior on both ends. Also, it has 3 turning points, and it has 4 x-intercept. Why it has 4 x-intercept? Because from the description of the dolphin path, we know that dolphin jumped out, so he crossed the x-axis. Then he dived in, he crossed the x-axis. Then he dived out again, so he crossed the x-axis. And then he went down in the water again, so he crossed the x-axis again. So 4 times he's crossing it. So we are supposed to have factored form with 4 terms. And we have to know the zeros of this function in order to write down the factored form. The zeros of the function are 2, 6, 10, and 14, according to the graph that we can see, right? This is point 2, this point 6, this point 10, and finally this is point 14, right? Because they're exactly in between of 4, 8, 8, 12, 12, 6, 12, 16, etc. These are the times when the dolphin breaks the surface of the water. Use the zeros to create the factors of a family of polynomial functions. Since the shape of the graph near each zero is linear, the order of each corresponding factor must be 1, right? So we have 4 brackets with the of a first degree, and we know that we have 2, 6, 10, 14 intersections. So we put x minus 2, x minus 6, x minus 10, x minus 14. And these are basically part of a factor of a polynomial family that we're just creating. But again, we don't know the leading coefficient. Again, using the graph, we can estimate the highest point when the dolphin leaped out from the water. According to the graph, we can see that the first point occurs roughly at 3.5, somewhere here, right? So we can substitute 3.5 into this function and get a corresponding y value, right? So now we know one point that belongs to this curve, which we are going to use now in order to find the leading coefficient of this polynomial, right? So we can use the minimum or maximum point as the known point of our graph, as we did in this example. Remember, we had one point that we know, and we used it to find the leading coefficient. Okay, so using that, you substitute x equals 3.5 into this formula. You know that y equals 0.5. You basically solve it for a, which gives us a negative 0.002, which basically proves that the end behavior is going to travel to negative infinity, and it also corresponds to the behavior of a dolphin, right? It dived up from the depths of the water, and he dived into the depths again. Now, simply substituting a into the factored form that we just wrote down will give us equation of a function that describes movement of a dolphin in the water. Isn't that cool? We just described the dolphin using mathematics. And imagine how much more stuff can you describe using polynomial functions. And finally, the summary. Key ideas. The zeros of polynomial function y equals f of x are the same as the roots of the related polynomial equations. F of x equals 0. Do you agree with me? To determine the equation of a polynomial function in factored form, follow these steps. First, substitute the zeros x1, x2, up to xn into the general equation of the appropriate family of polynomial functions of the form y equals a times x minus x1, x minus x2. And you see here, a, b, c value simply, if before we told you that it was a, b, c, now you could treat them as zeros of the function. If you're 0 at x1, for example, if one of the zeros is the x1, for example, equals 2, you substitute it into this formula and you get part of a polynomial function x minus 2, right? So you have 0 at x equals 2. Make sense? Substitute the coordinates of an additional point for x and y and solve for a to determine the equation. Right? We need to do this in order to find out the leading coefficient. If any of the factors of a polynomial functions are linear, then the corresponding x-intercept is a point where the curve passes through the x-axis. Right? If we have quadratic function for the certain x0, it would mean that the function has quadratic behavior around this point, or cubic behavior even. So if any of the factors of a polynomial function are squared, then the corresponding x-intercepts are turning points of the curve, and the x-axis is tangent to the curve at this point. Right? So now we know that if any factor in polynomial function has a square in it, it's supposed to be a turning point as well as the x-intercept. Okay? In this point, x-axis is tangent to the curve at this point. The graph has a parabolic shape near the x-intercept. If any of the factors of a polynomial function are cubed, then the corresponding x-intercepts are points where x-axis is tangent to the curve and also passes through the x-axis. The graph has a cubic shape near this x-intercept, right? You can see that in this interval, basically function behaves like a cubic function of the third degree, which has a following shape. We call it branches of parabola, right? Because by itself, these are left and right hand side of parabola, but looking different direction. Any questions about this part? I strongly recommend you to take a screenshot because these are key ideas on how to sketch polynomial functions. If you remember this, it's going to be a piece of cake for you. So let's say I give you 5 minutes to write this down and to copy it into your textbooks or make a screenshot, okay? Okay, guys. I hope I gave you enough time to copy this down. Any questions on the paragraph we just covered? Not at all? Good, good. So, transformations. Guys, let me know, what would you like to do now? Would you like to do a few practice exercises to the chapter we just covered? Or you would like to start the next paragraph related to transformations? It is deeply related to the one of the very first chapters we discovered when we talked about functions and transformations of functions. Remember, it was somewhere here. Yep. So basically this part, second. Yeah, basically the next paragraph is going to be similar to transformations of regular functions, but we're going to look into how these transformations are affecting cubic and quartic functions. Okay, then I'll just gonna choose exercises from here as part of your home assignment, and we're gonna move on to the unit 3.4, transformations of cubic and quartic functions. Basically, we're going to describe and perform transformations on cubic and quartic functions. What does it mean? It means that you know that cubic and quartic functions in standard form, cubic look like this, and quartic function looks like this, right? In the simplest form, this is x to the fourth power, this x to the third power, okay? This is their standard form. But what would happen, for example, if we add 2 to x to the fourth power, or if we multiply it by negative 0.25? How is it going to change the shape of the function that we're discovering? First of all, you have to remember the new form of notation for polynomial function. It's going to be as follows. f of x equals a times k times x minus d, bracket closes, exponent n, just arbitrary value n, plus c. Okay? So this is our general form for polynomial function, actually. And by changing a, k, d, n, c, you can get any polynomial functions that you're looking for. This is a general notation form. Okay? So now we can see on this graph that we have a standard cubic polynomial function, right? Just x to the third power. And then in the red color, we have transformed cubic function, because you can see the degree in front of the bracket with x is 3, which means this is a cubic function. This is how this related to this. Degree in front of the bracket in this type of notation represents the degree of a polynomial function. Okay? And we can see that we have this leading coefficient negative 0.25. We have this coefficient d equal to negative 2, and this coefficient c equals to 1, right? This is D in our function. K equals to 1 in this case. A equals to negative 0.25, and C equals 1. So I write A equals negative 0.25, K equals 1, D equals negative 2, because here it's plus, but in the formula we have minus D, right? So D should be equal to negative 2. And finally, C equals to 1, because we have plus in the formula. And of course, N is 3. The degree of the function is 3. And what each one of these coefficients gives us? First of all, let's look at this inflection point of this cubic function. You can see that for x to the third power, here's our basically point of symmetry or inflection point, right? And for transformed function, this point is going to be positioned here, right? Do you agree with me? That's basically visible on the graph. This is one point for a translated function, and this one for not translated one. First of all, I can see that this point is moved away from point x0, y0, right? Moved negative 1 to the left, sorry, negative 2 to the left in x-axis, and it moved positive 1 unit upwards. Do you agree with me? It moved negative 2 units to the left and 1 unit upwards, which corresponds to the coefficients D and C. So what coefficient D does? D is a coefficient that translates the graph in x-axis. If D is negative value, then the graph translated to the left-hand side. If D is positive value, then graph translated to the right-hand side. For an instance, before applying the rest of the transformations, our function is going to look like this. I'm going to use the blue color. So I took my blue graph and I translated 2 units to the left. Every point is 2 units to the left. And as a result, my graph would be like a copy of initial graph. It will be actually a copy, but slightly translated 2 points to the left. Do you agree with me? Now, C equals 1. C corresponds for y-axis translation, because wherever you get here, you at C, you translate wherever result certain amount of points upwards or downwards, depending on the sign of C coefficient. In this scenario, C equals to 1, so we're translating our function 1 unit upwards. So after this translation 2 units to the left, we're translating it 1 unit upwards. And as a result, let me use some other color. Okay, let's say red. Now, I'm translating all of the points 1 unit up. 1 unit up. This is 1 unit up too. This is 1 unit up. This is 1 unit up. And now joining those points would give me translated function. But take a notice that we don't get the final form just yet. We only got something close to the final red shape, and it's because we only applied translations to our graph. So we moved it only, but we didn't apply transformations, right? And transformations could be horizontal compression or stretch, and vertical stretch or compression. And also we are able to flip our function by using the leading coefficient negative number. If our leading coefficient is negative number, then our graph would change its end behavior to the opposite one. And in this example, we clearly can see that we have leading coefficient negative, which means that we are going to basically flip our graph, that is going to look like this. Let me use some other color so it will be more distinguishable, the green one. You see? And take notice that this green graph is not yet same to the red graph. Why? Because the green graph has more steeper rate of change, whenever the red graph has less steep rate of change. Can you see that? If I remove the green one, if I remove everything, you can see that the red graph is in fact, looks like it's more stretched in x-axis and compressed in y-axis. So you see this curve is more smooth than the initial function. And this is example of transformations that are applied to it. And let's take a look at what book tells us about it. Here you can see all the translations that we did together without any graphical calculator, but we did it by our bare hands. And looking into this example, last thing I can tell you is the leading coefficient, k, how it, this is a. So as soon as k in here is equals to 1, k responsible for stretches and compression in x-axis. For example, if k would be some positive value or just 2, 3, 4, then our graph, oh, sorry. Yeah, then our graph would have some kind of transformations in the x-axis. But as soon as k equals to 1, we have no transformations here, but a does not equals to 1, so we have some changes in y-axis. And as soon as a negative number and it's less than 1, first of all, we're going to flip our graph in the opposite side. And secondly, we will compress our graph in y-axis because a is less than 1. So if a is an interval from 1 to -1, we're compressing our function. That's why it's like more, has softer curve than the initial cubic function. I understand that it may be hard to realize at the very beginning, but remember that we already had this notation before, and you already learned each one of these coefficients and how do they affect the function. And when working with polynomial function, it's not much different. Okay? So describe the transformation that must be applied to y equals x to the third power to graph y equals -8, 1 over 2x plus 1 to the third power minus 3, and then graph this function. So first things first, when you see polynomial function like this, you have to recall how is the original form looks like. An original form has a times k times x minus d, and x has no multiple in front of it. X is solely x. So if in your formula you have 1 over 2 like this, you simply have to factor it out from the brackets in order to get a proper notation. Here, this is exactly what they did. They factored 1/2 out, but take a notice, not all the way out from the brackets, but inside the brackets, because brackets are of a third degree, right? We cannot simply factor it by 1/2. We should keep it inside the brackets. So now you can see that this notation is more like a form that we just discovered, right? Looks same. This is coefficient A, -8, k is 1/2. Let's write it down. A equals -8, k equals 1/2, D equals -2, and C equals -3. Basically, what we're looking into is a cubic polynomial function, right, of a third degree based on this exponent, the greatest exponent. So here we can see that vertically stretched by a factor of 8 and reflected in x-axis. So A responsible for stretches and compressions in vertical axis or y-axis, right? Vertical y-axis. K responsible for horizontal stretches by a factor of 2. You see, if we have k factor, it means we are stretching by a factor of the denominator. In the x-axis, not vertical, but horizontal axis for k. Once again, A for vertical for y-axis, K for horizontal for x-axis, and D and C, D for translations in x-axis, so basically moving in x-axis, and C for moving vertically in y-axis. Translations. These are all the coefficients that we have, but how do we basically describing the transformations? Pretty simple. First, we sketch the parent function, which is x to the third power. We sketch several points for it. For example, 5 points, right? Now we can sketch this graph. And now, after we get the parent function and its points, what we are going to do is to apply stretches and compressions. So A and K we have to account now. If K is 1/2, it means we are multiplying the X value by 2. If K was 1/4, we would multiply the X by 4. If K was 5, we would divide X by 5. Is that clear? Good. And finally, for y-axis, if A is -8, what we do, we multiply y by -8. What it does to our function is it's gonna get it inversed because of the negative leading coefficient, and it's also going to change coordinates for several points. So first of all, we perform the stretches, reflections, and compressions first. Multiply the x coordinates on the key points by 2, multiply the y coordinates on the key points by 8. So our key points are those points that we took for parent function. Now, the same points, we multiply them by 2 and -8, right? Now, y coordinate is determined by x times 1/2 brackets third power in front of a brackets -8, right? Now you can find new points for the transformed graph. Do you agree with me? And final stage, after you perform all the stretches and compressions, final stage is to apply translations. So we're doing translations at the very end. And this is fairly simple. We have to perform the translations last. In this particular example, where we can see coefficients D and C, we know those coefficients. So how do we perform translations? We subtract 2 from the x coordinate because D is -2, and 3 from the y coordinate because C is -3, right? From the y coordinate of each point on the red graph to obtain the corresponding point on the blue graph. So we take parent function, then we transform it, stretch, compress, inverse, etc. And only then we translate it. Okay? This is one of the approaches. The second one implies simplifying the equation first before doing anything else. In this scenario, we have another notation, which basically is same form, or as we had in the previous example, a times k, but it's simplified to as much as possible. You see, we still could get 1/2 outside of the brackets, but with a third degree exponent. Factor it with 8, and we'll get shorter notation, and a result is going to be absolutely the same, because we're simplifying the equation first. But steps are all equal to the solution A that we just covered. But you can also simplify your form. You see, result is absolutely the same as in here. The only difference is the formula that we get at the end. This formula is the simplified formula, and this formula is not simplified. Remember, simplification is not changing the properties of our graph because we're not changing the equality. Note that the final graph shown in blue is the same from the 2 different solutions shown above. 2 different sets of transformations have resulted in the same final graph. Determine the x-intercept of a function, blah, blah, blah. Guys, please take a look at this solution, because I'm pretty sure you were supposed to learn this in your previous classes on how to solve this type of functions. Okay? So please look into the solution, note it down for your future reference, because you would have to solve for x-intercept of a polynomial functions a lot, because this is how we find zeros of our function. Please take a moment to copy this down, and we're gonna move on to conclusion of our class. Okay, guys, sorry, I had to leave you for a minute. Is there any questions on how to determine the x-intercept of a cubic, a quintic function using algebra? Any questions at all? No? All clear about this? So again, we the main step is to let y be 0. Basically, that's how we're finding the x-intercept. Solving for x, simplifying. In this scenario, we have fourth degree. So we're taking as root of fourth degree from left and right hand side, which gives us two solutions for basically two lines of solutions, right? And each line of the solutions may have two roots. In this scenario, each line of the solution gives us single root, right? When x plus 6 equals 2, and when x plus 6 equals -2. Two lines of solution. In this scenario, for this polynomial function of fourth degree, we found only two x-intercepts, -4 and -8. Okay, I hope no questions about that. And the final summary, I strongly encourage you to write this down because it has this notation. So the polynomial function y equals a times k times x minus d to the power n plus c can be graphed by applying transformations to the graph of the parent function y equals x to the power n, right? A and k are horizontal and vertical stretches and compressions. D and C, horizontal and vertical translations, not transformations, translations. Remember that n could be any natural number or a whole number, integer, right? Because it's an exponent. And each point xy on the graph of the parent function changes to x divided by k plus d and y times a plus c. This is very important. How does the point changes? Please write this down. When using transformations to graph a function in the fewest steps, you can apply a and k together and then c and d together, as we did in one of the examples. What you need to know that in this notation, the value of a represents a vertical stretch and compression, and possibly a vertical reflection, if the leading coefficient is negative or positive. The value of k represents a horizontal stretch and compression, and possibly a horizontal reflection. Is that clear? A, vertical stretch and compression, possibly vertical reflection. K, horizontal stretch and compression, possibly horizontal reflection. The value of D represents a horizontal translation. The value of C represents a vertical translation. Is that clear, guys? Please note down the summary, and this is the end of today's class. I believe we did a great job. We covered 2 units today, and I'm gonna submit your home assignment to the Google Classroom for this unit and the previous unit today. Any questions about it?